Hello everyone, my name is Shakayla, and today I'm going to be talking about some major oxide modeling of the mono craters proposed by Ranee Johnson. These craters are relatively young compared to the others around it, like the Long Valley caldera and Glass Mountain. To study these craters, you must take into account the activities of the surrounding area. Because the craters are near these features, tectonic activity or magma intrusions and volcanic activity in earthquakes can affect what's going on in northern magma chambers. Ranee wants to study the size and depths of these magma chambers, try to foresee the magnitude of possible future eruptions. The data I'm about to show you is over 100 samples collected. They are determined to be mafic, intermediate, and classic, or a combination of the two. These samples were collected from monolake islands, craters, and monocraters. There are three different possibilities for such a volatile eruption: diverse magma compositions, more than one magma chamber, and different temperatures or heights of the dikes and so. This is a list of monocrater data samples and their major oxide compositions. I'll be using some samples to figure out which is the most primitive, as you will see in my graph later on. As you can see, it takes some trial and error, so I've had the samples of triangles. Here is where the calculations come in. This set of Excel calculation pertains to our fractional crystallization hypothesis. When oxide is less than 1, it is seen as incompatible in the middle, meaning it didn't mix well while it was in the middle. So the further away from the least it's compatible. The middle proportions also help better fit to my data as I can change the graph below. The bulk distribution coefficient is just another way of telling what's compatible or incompatible. Here at the bottom, for the calculated liquid composition, is where we will calculate concentration of some element in the middle. I've done 0.10 increments, 1 being the most primitive and 0.05 or 0.01 as being the most bulk. You can think of it as those that cooled and those that didn't and stayed at the bottom of the magma chamber. If you remember, I colored the data I tried out based on how they were plotted on my graphs in Excel. You can easily point out which samples are most primitive that way, which makes my search a lot easier. Equation. Now, this is the hypothesis for equilibrium crystallization. The set of data follows the same steps and methods, but in this scenario, every time a crystal is formed, it stays in the melt and tries to equilibrate instead of, say, possibly being kicked out of the melt. For our last hypothesis, mainly supported by Ranee, is magma mixing. Again, we use our parent magma sample, but now we're mixing it with another and we'll best showcase together. I try my best to say it right. Now to compare the graphs. In these graphs, you can tell which hypothesis would work best. The black line represents magma mixing, the purple line represents perfect fractional crystallization, and the green line represents equilibrium crystallization. As you can tell, some hypotheses work better than others. The reason I group together these positive slopes is because you can tell what's happening within the melt. If some crystals are formed and just sinking down to the bottom of the melt, or if some are floating. As you can tell from these graphs, some hypotheses are better than others, especially these three oxides. The crystallization, the fractional crystallization hypothesis and the equilibrium crystallization hypothesis both don't work here. As you can see, magma mixing takes to the front. Ranee later determined that there is possible different chambers because the first round of eruptions were intermediate to classic, while the preceding ones were more mafic in composition. As you can see in this graph, most of the monocraters are reliable, or you can see that they erupted on multiple craters and not just one, compared to the monolith islands of genetic results. Thank you.